Intel just did something that almost nobody thought was possible 3 years ago. They built the most advanced semiconductor node currently in production anywhere in the world, and they did it on American soil. Intel's VP of Advanced Technology Programs called these the most advanced semiconductor facilities not just in the US but in the entire world. That's a massive claim, and honestly, the data backs it up. This is the story of Intel 18A, what it is, why it matters, how it stacks up against the competition, and what it actually means for your next laptop, your AI tools, and the future of chip manufacturing. Let's get into it. Now, to understand why 18A is such a big deal, you first need to understand how bad things actually got for Intel. For most of computing history, Intel was the de facto chip company. Full stop. The benchmark everyone else chased. Then, around early 2010, things started going sideways in a serious way. Their 10nm node got delayed, then delayed again, then delayed some more. While Intel was stuck, TSMC quietly became the most important chip factory on the planet. Apple moved to them, then Nvidia, then AMD, and Intel's Foundry business started bleeding billions of dollars. And it didn't stop. As recently as Q2 2024, Intel Foundry posted an operating loss of $2.8 billion, up from a $2.5 billion loss the quarter before. That's not a rough patch. That's a company in serious trouble. So Intel made a bet, an all-in bet the company kind of bet, and they called it 5 nodes in 4 years. The goal was to compress years of delays into one aggressive sprint and come out the other side with a node that could genuinely compete with or beat TSMC's best work. 18A was always the target, the finish line, and they finally crossed it. Now, at the heart of the Intel 18A are two technologies that together represent the biggest shift in how chips are built in over a decade. The first is called RibbonFET. Quick explainer, no jargon. Every chip is made of billions of tiny switches called transistors. For years, these used a design called FinFET, where the gate, the part that controls the switch, touches the channel on 3 sides. 3 sides sounds fine until you're trying to pack hundreds of millions of them in a single millimeter of silicon. At that scale, current leaks, heat builds, and performance tanks. RibbonFET is Intel's version of a gate-all-around transistor. Instead of 3 sides, the gate wraps completely around the channel like a ribbon. RibbonFET allows for tighter control over electrical current in the transistor channel, enabling further miniaturization while reducing power leakage, a critical concern as chips become increasingly dense. More control means better efficiency. Better efficiency means either faster chips at the same power draw or the same speed at dramatically lower power. That trade-off is literally everything in modern computing, especially for AI workloads grinding away around the clock in data centers. According to Intel's full technical breakdown at the VLSI 2025 Symposium, 18A delivers a 30% increase in transistor density, speed chips up by 25%, or cuts power consumption by 36% compared to Intel 3. Pick whichever number matters most to your use case. They're all legitimately impressive. Now, what I love about RibbonFET isn't just the numbers, it's what it signals. The FinFET era is over. The whole industry is moving to GAA architectures now. Intel just got there first with an actual production node. Now, if RibbonFET is Intel's evolution, PowerVia is their revolution, and this one is a genuine world first. Think about how a chip is wired. Traditionally, both power delivery lines and signal routing lines share space on the front of the wafer. They're stacked together, competing for room, and the compression gets worse every time you shrink the transistors further. It's like trying to run a highway and a water main through the same pipe. PowerVia moves the entire power delivery network network to the back of the wafer. Backside power delivery frees the front side for cleaner signal routing and better performance. The backside metal layers are far thicker than the front side layers, resulting in lower resistance, better current capacity, and reduced RC delay, which lets signals travel faster and directly improves timing and frequency. The practical results are concrete. PowerVia improves standard cell utilization by 5 to 10% and ISO power performance by up to 4%, while also reducing voltage droop. Voltage droop is that instability you get when a chip suddenly demands a burst of power during an AI interference task, a gaming spike, whatever. Reducing that droop means more stable, consistent performance right when you need it the most. But here's the part that really gets me though. TSMC and Samsung have yet to introduce a similar backside power delivery technology, putting Intel in a strong position. PowerVia is in production today. TSMC won't have their equivalent until at least late 2026, more probably 2027, and that gap is real, and Intel is using it right now. But none of that matters if we don't know how it compares to TSMC's N2. So let's be straight about this, because the comparison matters and the picture is a bit nuanced. Intel's 18A achieves a Tech Insights performance score of 2.53 compared to the TSMC's N2 score of 2.27, and also outperforms Samsung's SF2 process at 2.19. On raw performance metrics, Intel is way ahead, but TSMC has a density advantage. TSMC's N2 is projected to offer considerably higher transistor density, around 313 million transistors per square millimeter, compared to the Intel's 18A at 238 million per square millimeter. More transistors per square millimeter means more functionality in a smaller chip, which matters a lot for compact mobile devices. So the honest answer is this: Intel 18A wins on performance and efficiency per watt. TSMC's N2 wins on raw density. Which one matters more depends entirely on what you're building. For AI accelerators and high-performance computing, where well-sustained efficiency is everything, 18A looks seriously compelling. For ultra-dense mobile chips, where space is the constraint, TSMC still has the edge. But here is what I think is the real win. There is a genuine race again. For years, there was basically one option for cutting-edge silicon, and now there's real two contenders. That competition is good for everyone, including you. Now, none of this matters without the actual product, so let's talk about what's already out in the world. At CES 2026, Intel launched the Core Ultra Series 3 processors, codenamed Panther Lake, the first compute platform built on Intel 18A, powering over 200 PC designs from partners worldwide. That's not a limited release, that's a full commercial rollout happening right now. Panther Lake delivers up to 60% better multi-thread performance compared to Lunar Lake at similar power levels, and up to 77% better gaming performance via its integrated Arc Xe graphics. 60% more multi-threaded performance at the same power budget. That's a generational jump, and it's in laptops you can buy today. On the server side, Clearwater Forest, branded as Intel Xeon 6 Plus, landed at MWC 2026, packing 288 DRAC-mount E-cores across 12 compute chiplets, with 18A compute tiles stacking on Intel 3 base dies using Foveris Direct 3D packaging. 288 cores in a single processor, built for hyperscale data centers running AI interference at massive scale. Clearwater Forest delivers a 17% instructions per cycle uplift over its predecessor on top of everything 18A already brings. And the customers are real too. Intel Foundry has secured commitments from Microsoft for its Maya 2 AI accelerators and from Amazon for custom Xeon 6 fabric silicon. When Microsoft and Amazon are placing orders, the technology is clearly not vaporwave. But here is the bigger picture that I think deserves way more attention than it usually gets. Intel plays a pivotal role in US semiconductor independence, with Washington holding a 10% stake in the company and backing it through the CHIPS Act. The geopolitical angle here is massive. The world's most advanced chips are almost entirely manufactured in Taiwan. That's not just a business issue, it's a national security issue, and every major government knows it. Having a legitimate, competitive, cutting-edge fab on American soil changes the equation in a real way. Intel's VP of Advanced Technology said volume production on 18A is going to kick off a decade of enhancement and improvement of RibbonFET and PowerVia, ultimately enabling what he called the 1 trillion transistor laptop. A trillion transistors in a single laptop. Think about what AI running locally on hardware like that could actually do. Now, Intel CEO Lip Bhutan confirmed that 18A will serve as the foundation for at least 3 future generations of consumer and server products, including secure enclave programs with the US government, which definitely isn't a one-time sprint. It's the platform Intel builds everything on next. Now, look, this all sounds fine and dandy, but Intel isn't fully out of the woods yet. Yield still needs to mature. The ramp is slower than originally planned. Lip Bhutan himself called 2026 an execution year rather than a growth year, placing Intel's real inflection point in 2027. There's still real hard work ahead, but here's where I genuinely land on this. What Intel put off with the 18A is undoubtedly remarkable. They took a company that was bleeding billions, years behind the competition, written off by half the industry, and built the world's most performance-efficient sub-2 nanometer node on American soil. RibbonFET and PowerVia are not incremental updates. They are architectural shifts the entire industry will eventually copy. So the comeback is undoubtedly real, the technology is real, the products are already shipping, and the next decade of chips in your laptops, your AI tools, your data centers is going to be shaped by the decisions Intel made right here in fabs in Arizona and Oregon. That's worth paying attention to.